Okay. Thanks for the introduction. Thanks for being here for this talk. I would like to present you high-level synthesis for machine learning. Just a brief outline of what I would like to walk through now. HLS4ML is a Python library that is intended for implementing neural networks, quantized neural network on FPGAs. So today I would like to present you a bit the workflow of the library. Then I would like to explain a bit what are the main compression techniques we usually use with the library. Afterwards, I would like to present some of the applications that exploits HLS4ML and some future developments. So I've been already very well introduced, but maybe I can just say that my career here at CERN is kind of uncommon, since I mainly work on knowledge transfer projects that are projects in which technologies at CERN are applied outside with other organizations mainly. I would like to give you a bit of context before starting with more technical details. In the last years, there has been a lot of research in the machine learning field for the performance, the predictive performance of machine learning models. And this leads to what you can see from this left plot in the slide. What I would like to ask you is, should we care just about the accuracy, like the performance, the predictive performance of this model, or are there any other important aspects to consider? For example, there are two use cases that I would like to highlight you. One is the experiments that are conducted here at CERN, in which data rates are very high, and probably such big models are not able to handle such very high rate of data. Another use case is, for example, a CubeSat, in which the computation has to be performed in a power-constrained environment. So HLS4ML basically supports all the flows, the most common flows for machine learning development, such as KRS, PyTorch, TensorFlow. And in order to make these models implementable on FPGAs, there are some compression techniques that I will present later on that are mainly quantization and pruning. After iterating at this level, there is a part that takes care of converting the project to an HLS project. The HLS is a C++ parameterized, is a C++ code with parameterized pragmas. And through HLS, there is the possibility to easily perform design space exploration, and also nowadays the tools are able to generate very high quality HDL code. By selecting some of the backends that HLS4ML has implemented, it's possible to implement the neural network on different supported FPGAs. So HLS4ML is based on a data flow architecture. This is basically the task-level parallelism paradigm, meaning that each layer is an independent computing unit, and each layer exchanges the data across the network through the use of FIFOs. It's important to say that the whole neural network is on chip. The only part that is off chip are the inputs and the outputs of the network. Another common architecture used in this context is the deep learning processing unit that you can see on the right of these slides. the main difference is that a lot of is off-chip in this case. On the FPGA, there is an implementation of a programmable application-specific processor, and so yeah, mainly the main difference is that there is a lot of exchange between the external memory and the FPGA. For the DPU, typically the quantization is homogeneous and fixed. Instead, for HLS4ML, it is tunable at per layer level. Why is doing? Okay, so just to focus a bit more on quantization. Quantization is basically a compression technique that aims to pass from a powerful representation to a more compact one. Computation accuracy is a bit problematic for neural networks. That's why they are trained with floating point data types. However, on FPGAs, it has been shown that fixed point data types are more efficient for resource and latency. HLS4ML supports two kinds of quantization. One is post-training quantization, that is the most straightforward. The trained model is quantized, in fact, after training. This is very easy to apply and to integrate to machine learning models, to neural networks. But it doesn't guarantee good performance for low bit widths, as you can see from the dotted line at the right plot in this slide. To overcome to this limitation, quantization-aware training is supported as well, meaning that quantization is considered at the training level. It's not that easy to integrate, in particular if you wanted to implement some particular kind of quantization. Also, it can slow down a bit the training, but it is shown on the same plot that for low bit widths it is much more efficient. Another technique is pruning. Pruning is basically the idea of removing redundant connection, redundant weights in the network. There are many different ways to perform pruning. We'd just like to mention two of them. One is regularization, that is a typical way of penalizing weights during the training. Another one is structured pruning that aims to removing contiguous blocks of weight. This is impacting, in particular in case of convolutional neural network, and it is basically filter pruning, in which entire filters are removed from the network. It is important to highlight that depending on how the model is implemented on the FPGA, if some resources, such as multipliers, are reused, pruning just one single connection can have no effects on the effective reduction on the resource consumption. This would work only in the case all the resources are fully enrolled. There is another interesting compression technique. This happens at the hardware level. As I said, the data are exchanged by using FIFOs. By default, HLS4ML set FIFOs to a predefined value depending on the input tensor. It has been shown, as you can see on the right plot in the slide, that the FIFOs are not typically fully exploited. The full length of the FIFO is not fully exploited. Through a calibration dataset and through RTL simulation, it is possible to profile effectively how many cells FIFOs needs, and in order to implement a model on the FPGA that exploits the whole length of the FIFOs. As you can see, there is a big reduction from these two floor plans before FIFO depth optimization and after. I would like now to show you three applications. One is from high energy physics from CMS, and the other two are from the knowledge transfer I cited before. So HLS4ML has been applied at CMS as an anomaly, for anomaly detection at the L1 trigger. It is based on a variation autoencoder trained on unbiased data. And yeah, it has been trained by using quantization-aware training, and it consumes very, very few resources. As you can see from the right floor plan, it's the purple part. And also the inference latency, it is very, very low, satisfying the requirement of the global trigger. We use HLS4ML also to submit an entry for the TinyML-perf context. As you can see from the table, we managed to achieve competitive performance for Cypher10 and Toy Atmos challenges. Cypher10 is for image classification, you can see from the right of the slide, and Toy Atmos instead is anomaly detection. Yes, it's an autoencoder for anomaly detection. Another application of HLS4ML is on autonomous vehicles. It has been conducted with Zenseact, a Swedish autonomous vehicle company. It is based on eNet network that is very similar to UNet. It is a segmentation, image segmentation network. We were focusing more on the latency, given the use case, and we managed to achieve 4.8 milliseconds per inference with a 10K parameter eNet model with homogeneous 8-bit quantization. The last one I would like to present you is related to Earth observation satellites we are currently working on. With other three partners, the University of Athens, Endurosat, and Agenium Space, we are working on a segmentation model for pollution detection in the oceans. The idea is to perform the computation on board instead of passing the images to the ground station, as you can see from the state of the art versus the edge space, that is the name of this project. That's why mainly, that's because the downlink bandwidth is limited, and so it's better to use it only for the necessary information. It is the model. It will be trained on Marida dataset that is provided by the Athens University. It is, as you can see from the right of the slide, it is a dataset of oceans images with the coast and with many classes such as island of pollutions and so on. For this use case, the latency is not the only requirement, not only the metric we would like to optimize. Also, the power is in the equation, let's say. So we are doing some considerations also in order to reduce the power as much as possible. At the moment, we are working with a knowledge distilled model from Agenium Space that has this tool for knowledge distillation. Knowledge distillation is another compression technique in which a pre-trained teacher model teach to a student the knowledge in order to have a student smaller knowledge, smaller model that is that performs in a good way, even if it's smaller. For the moment, we managed to implement the 10K parameter model for cloud. In this case, is another dataset, but will be very similar for the final case. for the cloud dataset, and we are working on some specific optimization in the HLS library to reach the 100K parameter. So I would like just to show you some future developments. One recent approach, like typically fixed point is used in the context of FPGAs, but recently, in particular for large language models, it has been shown that some custom floating point representation can be very effective. And so maybe this can be one way to research for HLS4ML. Another part, interesting part, would be to find let's say, a sweet spot between the data flow implementation of HLS4ML and the DPU. This would probably enable for bigger models to be implemented on FPGA by using HLS4ML. And as last, another project is to partition in a reasonable way big models in order to deploy them in a distributed fashion on different FPGAs by using a tool called Q1NX, that is quantized neural network exchange format. It is possible to estimate before synthesis what are the resources, the resource cost and the latency of part of the network. So that's it. Thanks for listening.
Okay, questions. I see one there.
Okay, thanks for your presentation. Currently here I am basically a frustrated user of HLS4ML. Just to explain a little bit the complications that I had is, okay, first I wanted to use HLS4ML in a non-PinQ platform. So meaning that back in the time, I had an Arctic 7 that I think is the 50 series, the one that with 50,000 logic cells, but I was unable to run the model that you sent to TinyML.
Okay.
Yes. So basically, when I was trying to do that, I faced a lot of issues with that documentation. So that would be a nice to have in.
Nice to have what in particular?
Okay. So going from the fact that I was not using PinQ, so I wanted to basically implement in this case the model in an Arctic 7 that is connected to PCI Express to another host that is an embedded system. So I was not able to basically synthesize the model. That was the first thing, but I managed to work around that. But at the end, I was not able to communicate. Okay. So in that sense, I made a framework, and that framework that is quite similar to PinQ, but in C. Okay. But at the end, I just collapsed with the other things. So
I think now we are working on extending what is the Vivado accelerator backend. Now we are going towards BITES support. This backend is intended for exactly implementing the part for the communication with the rest of the system, like for the system design integration. So I don't know when you tried, but maybe worth to check now if there is some. I think the support of this board is not yet present, but there is the whole framework. There is the framework, the backend to support it. So probably you can try to see.
The thing is the documentation, right? And
okay.
Let's talk in offline.
Okay.
But I will leave you with one question. Okay, there is another framework called FIN from AMD. Yes. So how HLS4ML differentiates from FIN?
Oh, well, I don't know FIN very well. I know that they share the architecture. I think they both have data flow architecture. I'm not sure if they are based on PyTorch models or Keras. Yeah, that's probably the main difference then, because I would say that HLS4ML supports Keras, the most Keras and QKeras. So maybe this could be the main difference. That's what I would say.
Yeah. Well, thank you very much for your talk. I had no idea that it was possible to implement everything in the FPGA, and that's very nice. I have one question. In case I want to use the tool you are working on, if there is any consideration regarding the architecture, I mean, that we have to think on? For example, I don't know, any limitation regarding the... Apart from the complexity, because I think that you mentioned something that for big models, maybe
yes.
It's not the ideal tool because everything will be in hardware. But maybe, I don't know, any other limitation like it's not possible to implement like multi-head attention layers or
yeah.
I don't know.
Yeah, actually, yeah, there is a library, like HLS4ML is capable of what is written in the library. There is no how can I say, there is not an automatic translation from the high-level machine learning to the HLS. Like if you don't have the HLS code written by someone that has expertise on HLS, that particular layer is not supported. So in that case, the approach would be to support that layer by implementing it in HLS and maybe open a pull request. That would be super cool for the community. And yeah, after that, if you integrate in the framework, in the system, that could be supported. Other than that, there are the limitations you pointed that are big models. Of course, for this data flow architecture are kind of limited. And yeah, thanks. Thanks for the question.
Other questions? Okay, if not, let's thank again the speaker.
Thanks.
So whilst he's getting mic'd up, I'll just say our next speaker is Shonny Summers.